All right, so we have to continue with our work, and we are still looking at the Journal of Mathematical and Computer Applications publication. It's a research article called titled "Mathematical Modeling of Alcohol Drug Concentration in the Bloodstream." So there is this person taking some beers, and then obviously there is alcohol in the beer, and then we now are interested in the concentration of that alcohol in the body and in the blood. So there is movement between alcohol between the two places in the bloodstream and in the body of the consumer of that alcohol. So now this is a mathematical model that we are not really pleased with because they didn't give us a proper introduction as to why we basically need this study, but we have got hope that their methodology is going to maybe present some sort of like novelty in their approach, in their analysis, in their research. That's what we are thinking. It was authored by three um, authors that are based in Nigeria, at the universities in Nigeria. And I think that it's through the model or maybe the simulations or the results that we are going to identify the contribution of this work to the body of knowledge. All right. So now we the last time we talked, we were focused on the formulation of the model. We have discovered that we're actually working at two places, and we, as I said, we're looking at the body itself, and so we had this movement that was happening to say, look, the body, there is movement of alcohol, alcohol from the body to the bloodstream, from the bloodstream to the body. So this gave us two vastage variables, all right? It's in the body, concentration in the body, or concentration in the bloodstream. And as a result, we end up getting two differential equations: the rate at which the concentration in the bloodstream changes as time is changing, and also the rate at which concentration in the body changes as time is changing. So those are the two differential equations that we are going to get. But again, I can see right here there is this excretion that is taking place, yes. But what I can see right here is the fact that um, we have got a linear system. Okay, we've got a linear system. So we've got a linear system here, which again, if we look at these dynamics, they tend to be nonlinear in most cases. All right, we want because this now becomes a more relaxed, simplified system, and it's nonlinear, which means that we might learn quite not much from this system. All right. And then now to set up the system, we are going to say, look, the rate at which the concentration here in the body changes with time is going to be increased by this movement from C2 to C1 given by K21. So K21 is positive. Yes, K21 C2 is positive because it's getting into C1, but there is something that is getting in out of C1, K1, 2, and K1 to C1 is getting out of C1. So we've got this is from C2 getting into C1, but then this is departing C1, and also there is a excretion that is also departing C1 there. And then we also have we have got what else do we have? We've got if we look now, we've got for C2, we've got from the body to the bloodstream. So this is addition. So K1 to C1 is positive, which is there. And then from there, we have got the negative, which is that part. But there is no excretion in C2. So yeah, that's what we have got. One of the things that you're going to see is that the rate of change in concentration, say the total concentration C, so this is now the total concentration of alcohol in your body. We don't care, is it in the bloodstream or it's in the body? It's just the total concentration. If we totalize that, I don't know if that will be important, but maybe we are trying to see um, how much alcohol stays in your body. So we are looking at it in total, as a sum total, and we're simply saying the CDT is going to be equal to the sum, where we declare or we define our C to be equal to, we are going to say C is equals to C1 plus what? C2. So it will be dC1 dt plus dC2 dt, like that. And if we do the math, we are going to see that K21 C2 is positive here, but it's negative here. So these two are going to cancel each other out. And also we've got this is positive there, negative there. And we are going to see that the answer we get here is simply minus KEC1. So in other words, you're simply saying as time changes, the rate of change of concentration of alcohol in your body is going to be decreasing. All right. In other words, you are going to remain sober as time changes. That's what this system is saying. All right. But now let's look at, we are given this system made up of equations 1 and 2, and I said this is linear and there is nothing interesting about the linear system, honestly speaking, if we can be honest. And now they say that we have got the concentration concentration in the body is given by D over V. And if you still remember, we actually defined our D and V as what? We defined our D as the alcohol drug dosage in both compartments, and V is also the volume of alcohol drug in both compartments. So that is the initial value of C, right? So we find that let me just write here and say that will be, so that will be what? That will be the alcohol. Let me see if I can write. I can't write. No, it's fine. So D is the alcohol dosage, and then the alcohol drug dosage, and then V is the volume of alcohol drug in the compartments. But then we also start with C2. We are simply saying that in the bloodstream there is no alcohol content concentration. There is no alcohol at all in the bloodstream. All right, that is good. So given that, then the authors went on to use the Laplace method. And one of the questions one has to ask himself is like, when do we normally prefer to use the Laplace method, right? Something that is very, very useful when you're analyzing, mostly in electrical circuits and some integral differential equations, when you're trying to convert those integral differential equations to algebraic equations. And this is what was done here. All right. And mostly engineers use this sort of method and for simulations, designs, that are crucial at crucial stages, in physical realization. So that's when the Laplace is normally used. And we actually have a Laplace formula, because this L that you see here is for Laplace. The L that you see there is actually denoting Laplace. So what can we say is the definition of Laplace in a nutshell? One of the formulas that we normally use under these circumstances is this one that I'm about to share with you just in a moment. Let me try to bring it to you. But then if you look at things the way they are, so you look at a situation, you look at the way, so I'm trying to give you this formula that I have here. So this is the formula that I will say, if I'm given a function t, f of t, then its Laplace is defined in this particular way, all right? That's why you find now that we have got to take the Laplace of every component in here, the Laplace of the derivative, Laplace of this guy, Laplace of that guy, Laplace of this guy. This is something that first year student can actually do. You can come with take that differential equation, transform it into Laplace. Like I was saying, that you've got to take an integral differential equation and then you transform it into an algebraic equation. So this can be done by first years without even hesitation. Worse, it is linear, because when you're taking Laplace transforms, you take term by term by term by term. So there is a Laplace for this in a table, So there was nothing much to actually write home about in this particular case. All right, that's why I say maybe as we go further, part of their methodology is going to reveal more stuff. But as things look right now, we are simply going to get two equations that are the same as this, and we solve them, then we get our solution, then we go. So the Laplace method that they used it gave us this system that we have got here, and we ended up with this system written as 7 and 8 that we can easily solve. So simplifying equation 7, we get this system that we have got here, and at the end of the day, you get solutions. So maybe the whole thing lies with what they did with the result. Maybe that's where the novelty is. But as far as this section is concerned, we have discovered again that we just used a Laplace transform, Laplace technique to make some transformations and then get some equations. And these are linear equations, so they can easily be solved. Let's wait and see in the next video what is going to take place. But so far, I'm not convinced that there is much that is going to come our way. All right. So this is the alcohol concentration model that we are dealing with, and we hope that we'll get something new. Okay, cheers.